Okay, just still waiting for some people. Hello, so we have one person here, looks like. Okie doke. It's okay, now we got 4, 5, 6, great. Well, thanks for coming over tonight, so to speak, I guess. What we're gonna do tonight is go through the study guide a little bit, and what I want to do is hit the high points, the things that I think are important for you to know, and you know, sort of good indicators of what I think might be happening on the midterm. So we have one person. Oops, hold on a second. There we go. And you are able to ask questions, and you should be able to see that on the side if you enable the Q&A there. And if you can't do that for whatever reason, you can also text me at 414-899-8269. And so we should be good to go. I'm just going to open up my study guide here. And the first thing that we'll want to be thinking about is the basic software development process and what the component activities of that development activity are. As I told you at the beginning, what we're really looking at is a reference model, if you will, for software development activities as part of an overall software engineering activity. And the reason that we're looking at them individually is that a number of different methodologies will put different emphasis on different activities. So depending on where you're working or what kind of project you're involved in, you may be spending more time in one of the activities than the other. Sometimes the projects are very elongated and there's a relatively slow harmonic. Other times, for example, in very extreme agile development projects, these may be very compressed and you may even omit 1 or 2 steps, but they're all still there. It's sort of like studying any reference architecture or reference model for something. All the parts are there, sometimes just arranged or colored a little bit differently. So you'll want to know the different component activities of software engineering, and that would include the activities that we talked about that one time, which is requirements elicitation, which would form the requirements for the system, understanding what they are, the analysis, you're forming the use cases, and understanding the domain. You're creating a domain model and the association between the concepts, and you're starting to create scenarios that allow you to understand what abstractions are taking part in a specific set of interactions within a use case and what their responsibilities are. And then we're going to cast it into system design and object design, where we start to think about how we're going to partition the system into different subsystems to make it a little bit easier to build or a little bit faster, depending on our architectural needs. And Then we'll be thinking about low-level design and implementation, which we haven't really gotten to yet in our lectures. But we did skip ahead a little bit to testing, because it's very important that we know how to design tests so that as we go ahead and start thinking about actually building these systems, we can determine if, in fact, the software is really testable. And so if you look back at the very beginning, we're thinking about what steps or what activities there are. And then there are process activities such as, or management activities such as communication, configuration management, and project management. Those allow us to manage those other activities and the resulting artifacts from those activities. So we have the development activities and the management activities. I think that's pretty straightforward from what we were talking about before. So feel free to jump in, with questions along the way, or if something, if I've missed something or it's not clear. If you can't ask it here, you can also text to 414-899-8269. I know it sounds like one of those fundraisers on the radio. So that beginning activity, that's pretty straightforward. The other thing I do want you to have a good feel for as we go along are the elements of the 4+1 view of architecture that we went over. It's a relatively simple model, but it's going to turn out to be a very powerful way of organizing our activities and our artifacts, the things we're building along the way, and providing a rationale for how we divide up the activities and make sure that we've covered functional and non-functional requirements in our system. So have an idea of what the 4+1, which is the use case model of architecture, is all about. There's the logical model, the development model, process model, and deployment model, and they're all unified by the use case model. We then went into some basic UML modeling, and we spent a little bit of time on that, in particular being able to create models plus the diagrams that represent them. I know that sounds a little abstract or ethereal, but remember, we're creating an abstraction of the use cases, and we diagram them and detail them by creating use case diagrams, which are the actors, the ovals, the system boundary, and then we create detailed textual descriptions of those specific use cases that tell us how it's fulfilling those functional requirements. We also create class diagrams along with class associations as part of our domain model, and we're also creating communication or interaction diagrams as a way of showing how objects at different levels of abstraction work together. So we have class diagrams and object diagrams. Remember, objects are instances of classes. That we create associations between the classes. They help us rationalize about cardinality between them, one-to-many, one-to-one, unknown. And they help us create a vocabulary of the different abstractions in the system. So the elements of UML that I would expect you to know are use case, class diagrams, and their associations, object diagrams, and the interaction diagrams, and the notion of a package, which is that ability to organize classes or objects into a package that looks like a little folder. So pretty much what we looked at in class there. Next thing is the basic notion of iterative development. Iterative development is the notion that we are going to start with basic parts of the system, and we're going to go through a series of development steps on a cyclic basis, so that as a spiral, the system starts to evolve as we continue to pass over it. As we continue to pass over it, we're continuing to extend it. Let's see, we have a couple of questions here. Let's see, I just saw it come in. Oh, here it is. There was a question about the different views in the 4+1 model. The logical view is our model of what classes of objects exist in the system, what instances of those objects exist and how they interact with each other and what their relationships are and how we organize those. The development view says, well, how am I actually going to implement those logical concepts? Am I going to put them all in one giant class file? Am I going to have a bunch of different class files? Are some going to be in Java, some in C++, some in a different language? Am I going to build libraries or jar files and then include those? So all of those sort of low-level development activities that tell me, how am I going to manage actually taking all those concepts and turning them into code? The process view worries about things like threads of control and processes and how those interact. We're going to talk about that later, and you don't really need to know that. And then the physical view or the deployment view says, well, where am I actually going to put those processes? Are they all going to live on one processor with multiple cores? Are they going to live on one processor with multiple virtual machines? Are they going to live on multiple processors with some channel of communication? And we're going to have to figure out how those processes that are executing the code that was developed in the development process, so the development view, that are implementing the logical view, and all of those are tied together by the single unifying use case model that says, well, the reason we're doing all this is so that these objects can interact to support some functional behavior in the system. Under requirements, you should know about the use case model, and that a use case model includes use case diagrams, and that would include the actors, the use cases themselves, the boundaries, and the relationships between them. Now, you don't have to get very fancy with them, but just the basic concept that we're using the actors to help us identify what's at the edge of the system. The use cases are helping us enumerate all the different functional behavior we want in the system. It's helping us identify where that boundary is. In other words, what actors are outside the system, what's inside the system. And the ones inside are going to help us define the scenarios. In other words, let's go through a scenario for what happens when somebody takes something out of an ATM, for example, or makes a deposit. And from that, we're going to start being able to model an object interaction diagram, and we're going to start having to think about, well, let's see, which behavior belongs with which object. Not necessarily which method at that point. We haven't really done that detailed design yet, but we're starting to think about, well, let's see. The bank is the one that's going to authorize the transaction. The ATM itself is going to actually dispense the cash and count it. It's going to print the receipt. The receipt printer actually will do the printing. And we start to partition out those responsibilities. Now, from that, what we're really doing, so we've created a use case model that includes not only that simple diagram, but also the detailed use case description that goes along with it, that is basically the textual description we saw an example of, which is the use case name and what happens in the use case and any exceptions to the scenario. And so what that's doing is it's helping us to model our requirements, and we can start to we start to examine the requirements thinking about what's functional and what's non-functional. Functional requirements are things that we expect the system to do to add some value. It's going to do something for us. Non-functional requirements typically are like adverbs. It's how that's going to do it. In other words, in what manner. Will it do it quickly? Will it do it securely? Will it do it reliably? All of those different kinds of factors. Will it run on a particular type of hardware? Will it be using a particular type of virtual machine? Will it use a particular library or something? Those are non-functional requirements typically. And they very often have something to do with performance or scalability or underlying systems that on which the system is implemented. Let's see. Next, we talked about the domain model. And if I ask you to sketch a simple domain model, what I'd like to see are sort of like the examples we gave for the air traffic control or for our chrono timer, which is the basic concepts in the domain. Remember, we're not doing detailed design at this point. We're not doing like a little class diagram of all the things we're going to build. We're thinking about what concepts exist in the domain, what responsibilities do they have? In other words, where's the behavior kind of allocated to? And what are their associations? So if I said, for example, that a plane has 4 engines, I would show a simple class diagram that shows airplane, engine, and the association between them. And let's see if I have Glyphy up right here. I'm not going to experiment, but you can look at ones from the slides or in the book that show simple domain models. And so you don't have to get particularly elaborate, but you would want to be able to show what those abstractions are, put the name in them, the associations along with any interesting cardinality, meaning how many are associated, if any, and whether they're a composite or aggregation. There's a question here. It says, in your ATM example, is the bank on the other end considered an actor? Yes, it is. And the reason for that is that it is going to cooperate with the system just like a human might. In other words, for example, if I send a message to a bank through a particular protocol and I say, hi, I'm this ATM and I want to make a withdrawal from this account, and I have identified and authorized this user, and I'd like to withdraw $20. Will you give me authorization for that? The bank would then turn around and say yes. But in terms of the system boundary, that is an actor outside who's going to just look like any other external source and receiver of events. So yes, the bank on the other end in the ATM example would be considered an actor. So sometimes they can be real people that are interacting through, say, simple user interface. The actor could be another system. It could be a device. It's anything outside the system boundary that's going to either supply an event or receive an event. Okay, I think I did that right. I think I'm learning how to use that Q&A thing. I hadn't used that before. The next thing that we'd like to take a look at is, I think that's pretty much all in domain model. One other thing, the primary purpose of the domain model is to make sure that we have a clear understanding of what the abstractions are in the domain, what their relationships are, cardinalities. It's, in essence, we're building, if you will, a dictionary of the system and a reasonable division of what their responsibilities are. Later on, as we start to do this system design, we're going to add more detail to them. Then we sort of skipped ahead a little bit and went to testing, which in the book is a little bit further along, but I brought it in because we usually think about how we're going to test the system early on. And in fact, in some methodologies, it's called test-driven design, or TDD, for exactly that reason. You write the tests first. In other words, a test is, in essence, an assertion of your requirement. And so test-driven design is really a series of asserting the details of your requirements. And the important things to know here are the differences between test plans and test cases, and then black box testing and white box testing. So test plans are the organization of what it is I'm trying to test. For example, if I was testing my ATM, I'd say, well, let's test the withdrawal of cash from standard checking accounts. And your test plan would say, well, I'm going to test withdrawals, and it's going to include only regular type withdrawals, and I'm going to require that I use the real machine, or maybe I use an emulator, and I'm going to run this version of the software, this build of it. And so I need to get all those parts. I need these emulators if I'm running an emulator, and I'm going to use Bob and Mary to do it because they're going to do the setup and the teardown. The test cases, on the other hand, are the specific tests that say, well, let's test withdrawing $20 from an account that has $1,000 in it. Let's try taking 500 out. Let's try taking 6 times 100. In other words, 6 interactions of $100. Let's try taking $1,001 out. Let's try taking exactly $1,000 out. So what we do is we start to think about, well, what are the real boundary values here? What are the interesting tests? If I can take 20 out, and I'd say, well, then I'm going to guess that 22 looks pretty much the same, and 61 looks pretty much the same, and I don't know, 110 is going to look pretty much the same. So we can say that a particular equivalence class of data is all the amounts between $1 and say $999 all look pretty much the same if I have $1,000 in the checking account. When I get to 1,000, I'm going to be left with $0. If I try and take out $0, what does that mean? Let's try that. Let's try and take out $1 million. How big of it? What if I roll over? So I'm going to come up with some boundary values. And so the test cases, I might have a number of test cases that I feel adequately test what the test plan is attempting to do, which is a nominal withdrawal from my ATM. I would then have a test plan, for example, for doing deposits. Or I might have a test plan for doing deposits and withdrawals. Typically, those test plans are going to be oriented around usually major use cases. That's usually the best way to do it. Otherwise, they just get too big. And black box testing is typically used for system level use case testing. In other words, I'm going to come up and I'm going to treat the system, the ATM, as I'm going to take out I'm going to do a deposit, I'm going to do a withdrawal, I'm going to check my balance, and I'm going to test out and see how it works. And maybe I'll do some stress testing. I'm going to try and do 1 million transactions. And so the stress testing starts to say, let's try and break this a little bit at the black box level. Now I can also do white box testing. Remember, that's where you know about what's going on. You know about the scenarios. You know about probably design documentation. You know the code, and you go, I think I know how to break this thing. In particular, you can start to look at it and think about, well, how many paths through this are there really? And we talked about the notion of the basis path calculation, or the cyclomatic number, which was the number of edges minus the number of nodes plus 2. And that was 6.2, as I recall. Nope. 6.1 maybe. Yeah. Hold on one moment just while I open that up. Sorry, I thought I had it open already. And there's 6.2. Give me one moment. And so if you look at the cyclomatic number that we talked about, Let's see. Oh, here it is. And so that's in the slides from week 6.2. And so the cyclomatic number is the number of edges minus the number of nodes plus 2. And that will tell you how many different paths there are. Now those nodes are going to be decisions, and the edges are the links between those. So starting at the first one, going through to the final one. And if you look at the examples from slide 6 in week 6.2, that's a good example to know. And so the reason you want to know that is it tells you how complicated your method is. And so in white box testing, we're looking at several types of coverage. One is we want to make sure we hit all the methods. In other words, each of the different methods that are supported by that object. And then we want to make sure that within a method, we're hitting all the statements. And we do that by making sure we hit all the branches. Now, here's where the subtlety is, hint, hint, is think about for each of those nodes where you have a branch, it may not be a single test that does it. You may have a compound statement. So for example, if you say, if A or B, then you have to test for both if A is true and B is true, A is not true, B is not true. In other words, you have to come up with the different combinations of test data that generate the different branches. So think about that. You can usually sort of deduce that simply by looking at it, but make sure you understand the example that we looked at in class where because you had a compound if statement there, you have to make sure you supply enough different test cases, going back up to what we were just talking about, enough different test cases to make sure you've exercised all the different branches. So we're trying to get that coverage. Now, that can sound a little tedious, and sometimes you're going to say, you know, I just don't have time to do that because we've got 12 minutes until the trading floor opens and off we go. But if you're doing supercritical real-time systems, you're going to go through each path and verify that you've hit it as part of your unit test. So that's considered white box testing because I know a lot about the internals. I know the documentation for it, I know all the code, I know everything that's inside it, and I know how to try and break it. Black box says simply, I know these inputs, some range of inputs, some domain of outputs, and as long as it does that, then I'm willing to accept the system. You'll remember that we had a quick discussion about different levels of testing, and that acceptance level testing says, hey, if it does everything the customer asked me to do and it doesn't break, then they can accept it. And even if there are other faults in that software, it's still acceptable. I know that sounds odd, but that's why it's called acceptance level testing because, well, the customer accepts it and it follows the requirements they laid out. Then if they want the system to do yet other things, well, that should be in the requirements. So we talked quite a bit about testing, and the reason we went through that in such detail is it starts to give us a lot of ideas about, well, man, how complicated should our system be? And we start to think a little bit about cohesion and coupling. And, you know, I forgot to put that, as I talked last night, I forgot to put that on the review guide, but you should have a notion of the difference between cohesion and coupling. Cohesion is the degree of dependency between collaborating objects. In other words, how much do I depend on other objects to make my stuff work? Cohesion is, do I have everything I need to do my job? I have all my data and my methods, and I work very nicely, and I have a minimum requirement I have a minimum dependency on other objects to get my work done. And so excuse me. So there's this constant struggle in the system between being not too coupled, but not overly. If you try and make it too cohesive, you wind up with one big ball, and it's too complicated. If you break it into too many tiny pieces, then you get too much coupling. So we're always battling this cohesion and coupling tension. And so when you think about cohesion and coupling, you want systems that are nicely cohesive and minimally coupled. But that's hard to do and still not wind up with just a few really big balls of code. So every time we try and decompose something to make it simpler, we're increasing the coupling in the system. So it's sort of like, you know, we've got a rotational, inertia trying to throw the rotating sphere out, gravity pulling it back in. So there's this dynamic tension between those two. Let's see, we have a question here for black box testing. Can you talk a little bit more about system level use case testing? So we're answering that question. I think that should show up. For black box testing, system level use cases are going to be the ones that are observed starting from the actors. Because what it turns out later on is we're going to see that we can have design level use cases. In other words, internally, we can keep that same model going in and just reducing the system, quote unquote, the system boundary down to smaller and smaller subsystems, and there's still little use cases within that. But really, a use case is intended to be exactly that. When Ivar Jakobsen, who is the originator of the concept of use cases, first talked about this, his notion was, this is how the system is used. Here's an example of it in use. And a use case is a collection of related scenarios or similar scenarios, or scenarios that all are part of the same use case with either different instances or different outcomes based on different exceptions. But basically, a use case is the initiation from an actor or the system, the interaction between the system and the actor, or actors if there's multiple actors in the use case, and the final product. In other words, from start to end, sort of the beginning. So in the case of our ATM example, the use case would begin when the user comes up to an ATM and inserts their card, identifies and authenticates themselves. The card is identifying them. The authentication is punching in your PIN properly with the card still inserted in the system. So I've identified and authenticated myself. And the bank says, yep, he's authorized to do something. And I select withdrawal. So in essence, I have two sort of use cases there. I have the identification authentication use case, which is then also part of the withdrawal use case. And so withdrawal says select an amount from a particular account. And if you have the right amount of money, I will dispense the cash. And if you take the cash, I'll print the receipt, and you take the receipt, and then I will return your card. And that's the end of the use case. So that would be considered a system level use case. Another one in there would be a withdrawal, a deposit, checking your balance, making a transfer. Each of those are initiated at the top level and result in a distinct separate value-added transaction with the system. You might have some other system level use cases that have to do with maintenance. For example, if somebody comes up and identifies themselves as a maintainer of the system, it might say, oh, well, I'm going to secure the vault, meaning it's going to lock up the actual cash box electronically, so that you can now open the door of the ATM. The cash box will be locked. You can't just open the door of the ATM and take the cash out. And you can then run tests. One of the use cases might be to load new software. Another one might be to run system tests on the printer and the display and all the other hardware, that kind of stuff. Those would all be system level use cases. And presumably, if all those pass, the customer would say, great, even though there might be faults in some of the objects that, had you done really detailed white box testing, you would have gone, ooh, well, none of their system level use cases ever touched that, so we're okay. Finally, the notion of design patterns. Oh, one other thing that is not on here is the notion of the facade pattern that we talked about for subsystems. And the reason that this is important is as we start to decompose the system and talk about what the responsibilities of these different chunks are, we'll say, for example, the ATM subsystem is responsible for dispensing cash, for printing a receipt, for doing identification and authentication. But the bank subsystem that I'm going to talk to, it's going to act as a proxy, if you will, with a boundary object, has a certain set of interfaces. And behind that, there may be a number of objects that we'll use to implement it, but we'll present one object that presents, in essence, a facade for all these other internal objects. And we use the compiler as an example in lecture. And it's also in the book. And that was an introduction to the notion of patterns. We also looked at what a pattern is. Remember, I said that there was nothing else you learned about design patterns, that a design pattern is a solution to a problem in a context. Meaning, here's a generic solution, and it solves here's a pattern solution. Here's a generic solution to a type of problem, and if you supply the context, I will solidify the solution based on that pattern. In other words, I'll actually instantiate it. So it's important to note that a pattern of solution can happen at a requirements level, it can happen at analysis level, at design, at implementation, at coding level, for example. And when you think about best practices, coding best practices, those are really patterns, aren't they? Somebody says, oh, I always indent my antecedent and consequence in my if statements. I indent them 4 spaces. And in fact, if you go into, say, IntelliJ or Eclipse, and you go in the little setup, the configuration, those are really all little coding conventions, aren't they? They're little patterns that you're instantiating and saying, oh, well, my indentation pattern is this, and my commenting pattern is this, etc. But typically, design patterns in particular help us to have a set of known solutions that work well to different types of problems, and then we go in and we match it up, the roles within those patterns. And so we looked at just a few simple ones to start with. Because of the funny way that we started the semester, we had that first day off when we started on Wednesday. We're actually 1 lecture different than we would normally be at the midterm. We looked at the notion of the command pattern and the memento pattern and the publish subscribe pattern, or the observer pattern, as 3 common patterns that we'll come across. So if you go back and briefly review those, the command pattern is one that makes it easy to encapsulate use cases in addition to general commands, but a command is an object. Memento was a way of storing state, enough state about an object so that it could be reinstantiated later on. And then publish subscribe, or the observer pattern, says when I have an object that I want to monitor for changes, when it changes, I want that object to tell me about it. So it's a passive way of doing it. Rather than constantly checking the object to see if it's changed, which would be very intensive, instead I say, hey object, when you change or you have a significant, an interesting state change, let me know. And it puts me in the list of all the objects that are interested observers. Can you also talk a little bit more about stress testing? Yes, I can. Talk a little bit more about stress testing. Excuse me, a little dry there. In stress testing, what we're doing is we're trying to find limits of the system. And let's see, I think I can actually share this screen. We're going to do a little experiment here. I know it's a little bit late at night to be doing this, but let's see, I think that should work. That's the slide about stress testing. What this says is we're looking for, it's sort of like boundary value, but here we're really stressing the non-functional requirements of the system by pushing it beyond its limits. For example, how fast can I push data at it? You know, for example, if data is coming in over a channel on a website, how many packets can I receive before I get an error that says, oh, I've exceeded my resource limits. So data limits, performance limits, frequencies, timeouts. I'm trying to stress the system in a way where, because I know about its construction, I can say, well, one way to really break this, for example, can I just put my finger on the keyboard and hang on to it for 10 minutes, for 20 minutes? How many keystrokes can I pile up before something happens? How big of a packet could I send? You know, an HTTP packet. If I'm uploading a file, what if I try and upload like a 64 gigabyte file? Is it going to break it? So that's the kind of stress testing that we do. That's sort of like, it's akin to, oops. It's akin to the nasty testing, and in the sense that you're trying to break the system by going beyond the bounds. Now, when I do like division by zero or the wrong input types or forcing the illogical path, you know, by forcing an odd path through a protocol, that's really more, you say, well, I know that there are boundary values that I'm going to try and test and see what happens. Whereas stress testing tends to be more performance and reliability type limitations. Here's a very common example for stress testing. I may sit and run the system without rebooting it, without doing anything, and I'm going to run what I consider to be a standard series of operations. For example, if I'm doing my ATM stress testing, I might say, you know what, I'm going to do it so that I'm going to simulate somebody doing a withdrawal every 12 minutes, and every sixth transaction is going to be a deposit. And I'm going to do that for the equivalent of 4,000 hours of operation and see if I get an error. And I'll start to measure my time. So there, I'm not so much testing, I'm looking to see what happens if I run the same operation over and over. I'm trying to simulate what it really looks like. They do this in the car industry. They'll sit there and they've got robots that will open and close the car door for days. Thousands upon thousands of open, close, open, close, open, close, open, close. Or if you go over to DCI in Waukesha, they have a giant metal table and they'll bolt their equipment. They make embedded computer equipment for like tanks and ships and stuff like that. They strap it onto this giant metal plate, and they've basically got a 6-cylinder engine that sits there and shakes it, and they'll let it shake for a week to see what happens. Okay, we're done with that. What is the format of the test going to be like? As in, will the questions be short answer, diagramming, or multiple choice, or a combination? Michael, the answer is a combination. Let me just stop. There we go. So there will be a couple of diagramming questions. So you'll want, you know, your basic UML. And, excuse me, let me stress that it should be the standard UML that we looked at, not just sort of a made-up version. There'll be some short answer, fill in the blank kind of things. In other words, single word answers. There'll be some short answer, sort of like describe this. Might have you write a test case, for example. So most of them will be fairly short. There's going to be 16 questions altogether for a total of 100 points. My suggestion would be that, and I'll try and remember to give this guidance tomorrow as well, do all the short answers, the multiple choice and short answer first, and go back and do the longer ones, so that you don't wind up running out of time for the other ones. Typically, everybody finishes in the right amount of time. It's not meant to run you up right against the clock. It's meant more to see, did you get everything we covered? Oh, and then there's going to be a little story problem that goes with it that 6 or 7 of the questions have to do with. So it'll take a few minutes to read through that. Take 4 or 5 minutes to read through. So you should have plenty of time. I think if you cover all those things, including the cohesion and coupling and the facade, you should be in good shape there. And then when we get back, we're going to crank on some more design patterns and start to really look at a bunch of detailed design stuff, states, interfaces, all sorts of cool stuff. Let's see. Any other questions at this point? I think we covered quite a bit here. This is sort of like the whole course in 42 minutes. I think that's about it. Well, if there aren't any more questions, I will see you all tomorrow at normal time, 11 o'clock till noon. There's I don't think there's a class in after us, so it should be okay. Oh, I know this is going to sound obvious. Make sure you bring a pencil or a pen to write with. Okay, have a good evening, and we'll see you tomorrow.